All right, today's lecture is going to be looking at specifically isotopes. Now, I know at the top it says atomic structure and the structure of the atom. We're going to go into more depth and detail in the next unit where we'll look at things like periodic trends and the arrangement of the atom and electron configuration, all that stuff that we've reviewed back from honors chemistry. But in this one, what we're mainly going to look at is just the basic configuration of atom, the three subatomic particles that make up the atom. As you can see up the top, there's a proton, neutron, and electron. And to mainly all the information that we get from the periodic table about all these different particles. The atom, again, if you remember at the top there, is the smallest particle of an element that retains a chemical identity. What that means is if you were to take and go a little bit further, the smaller than atom, if you go to a subatomic particle like a proton, if I have a proton from a carbon atom and a proton from a neutron atom, from a nitrogen atom, if you have a carbon atom and a nitrogen atom, if you were to take a proton from a carbon atom and a proton from a nitrogen atom, you could not identify them as being the one that came from the carbon and one that came from the nitrogen. So the smallest unit of matter that possesses a specific set of properties, that is an atom. Okay. Cathode rays and radioactivity, that was stuff that we talked about in honors chemistry, something that is just not very important, so I'm just going to bypass that. Again, you must know that protons are positively charged, electrons are negatively charged, and neutrons have got a zero charge, and they're often symbolized by what I just put there up at the top. Okay. If you have something that is an atom, if you have an atom, what that tells us is that the number of protons is equal to the number of electrons. The number of protons and electrons are equal. Atoms are neutral particles, and therefore they do not possess a charge. Okay? If the protons and electrons are different, if we have more protons than electrons, we are going to have a positive particle. And that positive particle is called a cation. Okay, a cation. And vice versa, if the electrons are larger than the number of protons, if we've gained an electron, we have a negatively charged particle, and that is called an anion. So these are ions. When we have oppositely charged, when we have protons, electrons, we have a difference in charge, we develop the charged particle. That charged particle in general is called an ion. More specifically, cation and anion for positive and negative. Okay. Atomic number is the number of protons and neutrons in the nucleus. All of the mass comes in the nucleus of an atom. Electrons, their masses are so small that they're considered negligible. So all of the mass of an atom is considered to be in the center. And if you remember back, the model that we most know is called Rutherford's model, which is the empty space model, which we have the tiny, small, dense, positively charged nucleus, and we've got the big, huge, large electron cloud that circles around it. That is called the empty space model. Now, this model that I just drew is not justice at all. The electron cloud would be much bigger than the size of my iPad right now if the size of the nucleus was such. If the nucleus that big, it'd probably be the size of Marshfield Senior High School. Okay, so most of the atom is empty space. However, all of its mass comes in just that small, dense, tiny nucleus. So the mass number is the total number of protons and neutrons in the atom, because that's where all the mass comes from, is just those particles. An isotope, which is the focus of this lecture, is the same element but it has different mass. So for example, if I have copper 63 and copper 60, back up there, and copper 65. These are the two naturally occurring isotopes of copper. Copper has more isotopes than those two, but these are the only two that physically occur in nature. Okay? What's different between copper 63 and copper 65? Well, first of all, what's the same? Since both of the elements is copper, they both have the same number of protons. Now, where do we get the number of protons from? We must look at the periodic table. And if you look right here, copper right here is element number 29. That number that is above the copper symbol, that is called the atomic number. And the atomic number is the number of protons in any copper isotope, ion, you name it. Any particle of copper will always have 29 protons. So for these two isotopes, they both have 29 protons. The number that follows the hyphen, this is called the mass number. And that's simply the total number of protons and neutrons. And therefore, if I know the protons, the neutrons must then account for the other additional part of mass. So if I subtract the atomic, if I subtract the mass number from the atomic number, that'll give me the number of neutrons. So 63 minus 29 will give us 34 neutrons. Copper 65 has 2 more units of mass, which means it has to have 2 more neutrons, so it has 36 neutrons. So there is roughly a ratio of protons and neutrons that creates stable isotopes, and that usually is about 1 to 1. So most stable isotopes have a proton to neutron ratio of 1 to 1. As the elements start getting bigger, as we get closer to the bottom of the periodic table, the ratio gets closer to 1 proton to every 1.5 neutrons. So as we get bigger elements, we need more neutrons to keep the isotope stable. But it's usually that window of 1 to 1 to 1.5. All right. So being able to account for the number of subatomic particles is very important. It's something that a few years ago I expected my students that they kind of knew that already, but I later learned that I do still need to go over that and try to bring that back to the forefront of your memory. Okay. How do we measure the masses of atoms? We measure them in something called an atomic mass unit. An atomic mass unit is really defined as 1/12 the mass of a carbon-12 atom. A carbon-12 atom contains 6 protons, 6 neutrons, and 6 electrons. If you take the mass of a carbon-12 atom and divide it by 12, that is what an atomic mass unit is. Okay? Because there is a little bit of mass with an electron, for the most part negligible, but when we start looking at very small units of mass, it does account for a small little bit. The only isotope that has a whole number assigned to it is carbon-12. The atomic mass of carbon-12, one atom of carbon-12 has a mass of 12 AMU. Exactly. All other isotopes have masses that are a little bit above or under their mass number. For example, copper 63, its exact mass is not 63 AMU. It's around 63. I believe if you look it up, it's like 62.926, something like that it is, AMU. So the exact mass is a number that's extremely close. When you would round it, you'd be able to round it to its mass number. Okay? And that's just based on definition. Something that's not really all that important that you know. I just wanted you to know where it comes from. Atomic weight is the average atomic mass of an element. Now, when I have a pile of carbon, not all of the atoms in that pile of carbon are identical. Okay? What we find out is that there are isotopes of carbon-12, there are isotopes of carbon-13, and there's isotopes of carbon-14. Okay? Because there is multiple types of naturally occurring isotopes of carbon, the atomic mass of carbon is not going to be exactly 12, 13, or 14. Okay? What we have to do is take a weighted average of these numbers. And I believe about 98% of all the carbon is carbon-12, 1.2% is carbon-13, and carbon-14 is about like 0.8%. That's probably it's in the ballpark. It's not exact. So, how do we get the atomic mass of carbon-12? If you remember that, we go back to the Candium lab. If I know the percent abundances, the first thing I do is I got to move the decimal point. Once you convert the percent abundances, you convert it to something called a relative abundance, which is the decimal value or the ratio accordance to 1. If once you convert the percent abundance of all the isotopes, so 98% of all the carbon atoms are carbon 12, the relative value of that is 0.98. We multiply that by the mass number of each of the isotopes. And once we have these numbers, which I don't have on the top of my head, once we have all three of those numbers, the last step is we add them all together. And when we do, we get a number that's about 12.01. This is the average mass of all of the isotopes added together, considering how abundant they are in that pile. So the atomic mass of an element is going to always lie closest to the isotope that is the most prevalent. In this case, carbon 12 is by far the most prevalent, and therefore the mass of carbon is going to be very close to that of 12. Okay? So the closer you get to, now copper, as I said before, has two naturally occurring isotopes, 63 and 65. If you look up the number below the carbon atom, okay, which is 63.55, this number below the element symbol in the periodic table, this is the atomic mass. And this is that weighted average, just like carbon on the bottom. This is the weighted average of, in this case, the two naturally occurring isotopes of copper. 63.5, if I think of a number line, this being 63 and this being 65, 64 is in the middle. 63.55 lies closer to 63 than it does 65. Because of that, what I know is that copper 63 is the more abundant of the two isotopes. There's more copper 63 in the world than there's copper 65. Okay, so that's some information you can get from isotopes and their relative abundance and atomic mass. All things that you need to know for this section. Okay. The last thing is just looking basically at the periodic table. I really like this periodic table that I found this summer when I was developing this packet. And you can see here the different substances that are classified as metals, metalloids, and nonmetals. For the national exam, when you're given your Chem Helper, one of the first things you might want to do is take your pen or pencil and right by boron, start the red staircase. Oh, I wish that was a little bit darker. And draw in the red staircase. I apologize, it's not really dark. I'll probably come back and just do it with my black pen. Oh, let me try now the red with this one. There we go, that's better. I was on the wrong marker. So if I draw in the red staircase, now obviously it doesn't have to be red for you, just draw it in. This can help you identify that main area which separates the metals from the metalloids and the nonmetals. Metals are to the left staircase, except you cannot forget about hydrogen. Even though it's to the left staircase, hydrogen is an oddball. We position hydrogen in the first group mainly because it has one valence electron. But property-wise, hydrogen matches none of the other elements in the periodic table. The only reason it's there is because of its configuration. All of the other elements in group 1, these are called the alkali metals. Okay, alkali metals. That's the first group of the periodic table. Hydrogen is not part of the alkali metals because hydrogen is not a metal. But the group 1 is the alkali metals. They all have very similar characteristics and properties. Elements in the same family or vertical column tend to have similar properties. Hydrogen is just an oddball. It has to be positioned somewhere, so they just put it there mainly because of it having the similarities of group 1 where it has one valence electron. The second group is called the alkaline earth metals. Group 17 is called the halogens, and group 18 is the noble gases. Again, you're not going to be given questions in the national exam that's like, what do we call group 18? But it just is important to kind of know. A lot of times I will talk about the families and I'll use those names just so in these lectures you know what I'm talking about there. The periodic table is also numbered from group 1 all the way to group 18. We do not use these A and B designations. That's one thing that I do not like about this. So on the national exam, you're not going to have any of those B or A designations, so you can just kind of cross those off. So we go from group 1 all the way to group 18. Okay, the bottom block here in the periodic table, these elements, there's only 2 atoms in each family. They are not given a group number just because it's only 2 elements. And most of these elements don't exist for very long periods of time anyway. So there's 18 columns or families in the periodic table. 4 of them are named that you might be aware of. So groups are vertical. Horizontal are called periods. There are 7 periods, 1 through 7, horizontal rows, and there's 18 vertical columns. Okay. Last thing, metals, nonmetals, and metalloids. Metals. What are some properties of metals? So real quickly think about them. Okay, metals are shiny. They have a high luster. Okay, they are malleable. We can bend them into shape. We can pound them into a shape. They are very conductive. Okay, they have a high tensile strength, meaning that we can stretch them into thin wires. And when it comes to their valence electrons, they have a low number of valence electrons. They have a low also coulombic attraction. The valence electrons are quite a distance away from the nucleus. There's a low coulombic attraction to them, and what that causes is metals tend to want to lose its valence electrons. These are all properties of metals. Nonmetals is exactly the opposite. A nonmetal is not shiny, it's dull. It's not malleable, it's brittle. They're not conductive. They have a low tensile strength. They snap. They can't be drawn into wires. And they have a high coulombic attraction, which means they don't lose valence electrons. They have more of a tendency of gaining electrons. So again, metals tend to lose valence electrons. Nonmetals tend to gain. The metalloids, which fall along the staircase here in orange, the metalloids is that transition point from being a metal to a nonmetal, and that those elements tend to have combinations of both. The most important thing to know about metalloids is that they are semiconductors, which means they only conduct under certain limited conditions, which makes them very valuable because they only conduct when we want them to connect, and therefore they're used in circuits and electronics quite often. Okay, so that's just a general basic information I wanted to get across. The main key point is the isotopes, and then also just to go through some of the key parts of the periodic table where to find different elements and just to know the organization of the periodic table. Okay, let's turn the page. If I go back to the previous periodic table and I find gold, I can see that gold has an atomic. Now on this page, what I'd like you to do is I'd like you to complete this. This is your homework for this lecture. So I will complete this page and put it online. Your job then is to complete this and then check the answer key over, and if you have any questions, please contact me. But don't think this is above you. This is very important information to be able to do and problems to be able to solve. The first problem is filling out the table to look at the number of electrons, protons, and neutrons of each of the different isotopes that are present. The 3 problems below that are atomic mass problems. Again, to do atomic mass problem, we have to move the percentage symbol, make it a relative abundance. We have the atomic mass units. We have to multiply those and add them together. Now, some of the problems, like this first one, is going to follow like the example I gave with carbon. But a couple of the other problems down here in 3 and 4, specifically 4, the answer is not quite as easy as that. You might have to go through some just information to read through and how to do those type of problems. Okay? Actually, now as I'm reading it quickly, mathematically, it's not a problem you'll have to worry about. It's actually more of conceptual problems. So I might give you a harder atomic mass problem the next time I see you in class, just to kind of have you do it backwards, where it's not as simple as number 2 and following the steps, just to kind of review that with you guys. But otherwise, there's some key concepts. And then down below, we have a couple of short answer questions I'd like you to answer. Okay? So let's just do the top one for you, and then I will stop the lecture here. So the first one we see here is gold 197. Now there's two ways of showing isotopes. You can put the atomic symbol and then have 197, or you could have the atomic symbol and put the mass number at the top leading off before the atomic symbol. And then sometimes they might put a subscript there, they might not. The subscript is the atomic number of 79. So they don't have to give that number 79 because you are going to have access to the periodic table. You can look it up. So sometimes in this nuclear notation, they will give you the atomic number in the bottom, but they don't have to. Just understand that the bottom number will always be the atomic number for the element, which you can look up in the periodic table. The number above is the mass number. The reason why we show it like this is then we can easily subtract the atomic number, the mass number from the atomic number, and doing that will give us the number of neutrons. So I know that the number of neutrons in gold 197 is 118 because I'm able to subtract the atomic number from the mass number. Gold 197, its atomic number is 79, and the atomic number is always the number of protons. And because there is no charge, if there is no charge in isotope notation, you would see if there's a charged particle, an ion, there'd be a charge to the upper right of gold. Since there is no charge present there, then this is an atom. So that tells me that the number of protons must equal the number of negative charge particles, the electrons. Okay? And then we could write this in the hyphen notation, which is gold 197. So this is called hyphen notation, where the mass number follows the atomic symbol, or we could write it in nuclear notation where the mass number leads off and is to the upper left of the atomic symbol. Okay, so down below, I want you to complete the table and answer the following questions and check those over in Canvas to see how well you did on this stuff. Again, if there's any questions, just talk to me. Thanks for listening.